In this section, we're going to look at L'Hopital's rule and start talking about limits in general. So we're going to apply L'Hopital's rule, compute limits using L'Hopital's rule, and then talk about dominance of different functions using L'Hopital's rule, something that we've talked about in chapter 1 before. So let's introduce this rule. If f and g are both differentiable functions, that means that the derivative exists, and the limit as x approaches a of f over g is indeterminate of the form 0 over 0 or infinity over infinity, then the limit of f over g is equal to the limit of f prime over g prime. So let's say that again. Let's talk about a couple of details here. When we plug in a into the functions, we get f of a over g of a, and that gives us 0 over 0 or infinity over infinity with maybe a minus in there. If we have that, then that's when we are able to use L'Hopital's rule, and that's the only time we're going to be able to use L'Hopital's rule. By the end of this section, we're going to find that L'Hopital's rule is a pretty nice way to deal with a lot of limits, and you're going to want to use it for a lot of different cases. Know that it is only in these two cases, and we need to check that we have 0 over 0 or infinity over infinity each time before we use L'Hopital's rule. Another thing to keep in mind is, what are we doing in the rule? We're taking the derivatives of the top and the bottom function separately. We are not using the quotient rule. It is not the derivative of f over g, which would be f prime g minus f g prime over g squared. So we're not doing that. We are doing the derivative of the top and the bottom separately. And then another thing we're going to keep in mind is that we're often going to use L'Hopital's rule more than once. We're going to use it one time, plug in a, and if we get 0 over 0 or infinity over infinity again, we can reapply the rule. We can keep on doing that until we get a number. And this is going to be most useful when we're talking about derivatives of polynomials. When you take the derivative of a polynomial, you decrease the degree by 1. So if you do L'Hopital's rule enough times, that polynomial will just vanish into a constant or 0. And we'll see that at work in an example. All right, so keeping these things in mind, let's talk about why L'Hopital's rule is true. And to do this, we're only going to look at the 0 over 0 case. The infinity over infinity case is much harder to understand, and it's just very technical. But I think we can kind of understand why it's true in the 0 over 0 case. So if that limit, f over g, is equal to 0, then that means that f of a equals 0 and g of a equals 0, like we said on the previous page. And how we're going to show this is true is we're going to use the fact that we can estimate the functions f and g using the tangent lines of f and g at x equals a. That means that f of x is going to be about f of a plus f prime of a times x minus a near x equals a. And same thing for g of x, just using its tangent line. This is only true near x equals a. And we know that f of a and g of a are equal to 0. So we can get rid of those terms, and we can say that f of x is going to be about f prime of a over times x minus a, and same with g of x in terms of g. So that means that near x equals a, we have f of x over g of x is going to be about f prime of a times x minus a over g prime of a times x minus a. And we're going to say that we can cancel out the x minus a's when we are near, when x is not equal to a. And then we get f prime of a over g prime of a. So a function over function is now kind of look like a derivative over derivative. And that's where we get our rule. Note that these approximations become equality when we have the limit as x approaches a, because we're saying let x get as close to a as you possibly want. These things are no longer approximately equal, they are exactly equal. This should read x approaches a, not 0. Got to approach the same value each time. So let's see it at work. We need to check that we can use L'Hopital's rule, take the derivative, and then we have a brand new limit problem we have to take over again. So in each of these problems, we're going to start with by plugging in that value in for x. This is going to give us sine of 0 over 0, which is 0 over 0. That is one of the forms that we can use L'Hopital's rule. That's an indeterminate form, but now we have a tool that we can maybe use there. So we're going to use L'Hopital's rule. And I'm going to just write that as L'H. We're going to use that rule, or maybe L'H OP, L'Hopital's rule. So that means that this limit is equal to the limit of the derivative of sine over the derivative of x. Taking those derivatives, we have the derivative of sine is positive cosine. The derivative of x is 1. And this is a brand new problem. And we have to deal with it just like it was the first thing we were given. Plug in 0 in for x, and we get cosine of 0 over 1, which is 1 over 1, and that's 1. And that is a real number, so that is the answer to our limit. So we turned 0 over 0 in indeterminate form using L'Hopital's rule into something that we can determine the answer. Let's do it again, this time with a limit at infinity. So let's think about, first of all, quote unquote, plugging in infinity in for x. If we do that, we have 3 infinity squared minus 1 over 4 infinity squared plus infinity. And that's going to just go to infinity over infinity. The top gets really big, the bottom gets really big. There's our indeterminate form. But it's one that we can use L'Hopital's rule on. So we have that this limit is going to be equal to the limit as x approaches infinity of the derivative of the top over the derivative of the bottom. Notice that I'm writing equals limit x approaches infinity on each step. We have the derivative of the top is going to be 6x minus 1, and the bottom is going to be 8x plus 1. And sorry, not 6x minus 1, just 6x. Derivative of negative 1 is 0. All right, brand new problem. So we're going to plug in infinity in for x, and we get another infinity over infinity. So we're going to use L'Hopital's rule again. We can use L'Hopital's rule more than once. This is like a brand new problem, and you can use L'Hopital's rule in a problem. So this is going to be equal to the limit as x approaches infinity of the derivative of 6x over the derivative of 8x plus 1, which is equal to the limit as x approaches infinity, 6 over 8. And that limit is, again, we have a brand new problem, but this is just a constant. This is just equal to 6/8. Maybe we can write that as 3/4. And that is our answer. So a few things about this last problem. Note that we could use L'Hopital's rule more than once, and each time we used it, the degree decreased by 1 in those polynomials. So because we had degree 2 polynomials to start with, 2 applications of L'Hopital's rule got us down all the way to the end. This problem doesn't have to use L'Hopital's rule. We know that this limit is equal to 3/4 by properties of rational functions. That's the horizontal asymptote of a rational function, where the degree of the top equals the degree of the bottom. So we could just say that, and it would work. But L'Hopital's rule is another way that we can kind of deal with it. Or maybe you can think about L'Hopital's rule is a proof of why that rule works with rational functions. All right, onward. We are going to encounter other indeterminate forms when we're dealing with these limits. But note that we have to have 0 over 0 or infinity over infinity to use L'Hopital's rule. So when we encounter some of the other indeterminate forms, we can manipulate the expression algebraically to try to turn it into the form of 0 over 0 or infinity over infinity so that we are able to use L'Hopital's rule. Again, L'Hopital's rule is going to be a nice tool to use. It's going to be useful for us to use it. We want to try to find opportunities to use it. So there's going to be a couple things that we can kind of say are general ideas. Note that there may be problems that don't follow some of these descriptions. This will take care of most everything. So let's say that we got the indeterminate form 0 times infinity. It's an indeterminate form, which means that you cannot say anything about the answer one way or the other. You have to manipulate something algebraically. This is going to be like a function times a function, f times g. And the algebraic manipulation you can do is to write it as a fraction, f over 1 over g. This is the opposite of when you divide, you multiply by the reciprocal. This is saying when you multiply, you divide by the reciprocal. So that's going to be a tool we can use to deal with 0 times infinity. The next one we're going to talk about is infinity minus infinity. That is an indeterminate form. And this is going to usually come about when we have 2 fractions to deal with. And the goal is going to be to combine the fractions using common denominators, turn it into just one fraction, and hopefully that's going to be 0 over 0 or infinity over infinity. And then there's a host of these exponential indeterminate forms, 1 to the infinity, 0 to the 0, infinity to the 0. And we are going to use the log trick, that's what I'm going to call the log trick, to take care of those problems. That means that we're going to take the natural log of the limit, and we're going to use our log properties to simplify the expression, usually to take the exponent out in front. But note that when we do that, to get rid of the natural log, we have to take e to the power of whatever we have at the end. Another way to kind of do this, and we'll show both ways in an example, is we could take e to the natural log of the whatever and then use log rules. So what am I talking about there? We're using the fact that x is equal to e to the natural log of x. This is the log trick that we can use this fact. And then we're going to use our log rules that if you have natural log of x to some power, you can write that as a times natural log of x. Exponentiation becomes multiplication. Also, if you have 2 things multiplied inside of a log, you can write that as addition. And division becomes subtraction. So we're going to use these log rules after we do the log trick to take care of these limits, and we'll see an example of that. All right, so here's an example. The limit as x approaches 0 from the positive direction of x natural log of x. When we, quote unquote, plug in 0 here, when I plug it in for x, I get 0. And when I think about what's the limit as x approaches 0 from the positive direction of natural log, it might help to know what the graph of natural log looks like. And as we approach 0, we are going down to negative infinity. So this is like 0 times negative infinity, or it's at 0 times infinity. And that is an indeterminate form, but we cannot use L'Hopital's rule yet. So we're going to do our step of writing this as the division over the reciprocal of something. There's two different ways you could do that. One is you could write this as natural log over 1 over x. When you multiply by x, that's the same thing as dividing by the reciprocal. We don't usually say that rule, but it's the exact same thing as division is the same as multiplying by the reciprocal. Notice now, when we do this limit, when we plug in 0, when we plug in for natural log, we know that's going to be negative infinity. We did that before. But when we plug in for the 1 over x, that whole function, the limit as x approaches 0 from the positive direction of 1 over x. It might help to know what that graph looks like. 1 over x, we approach 0 from the positive direction. That's going up to positive infinity. That's an indeterminate form, but we are able to use L'Hopital's rule. So that means that we are going to take same limit, but we're going to take the derivative of the top and the derivative of the bottom separately. And this is going to give us 1 over x, the derivative of natural log, and the derivative of 1 over x is negative 1 over x squared. So this is a brand new problem, and we need to tackle this problem just as we did any other limit problem. The first thing that we should maybe try to do is to plug in 0 in for x. If we do that, we're going to get infinity over infinity again, and that's an issue. So we could do L'Hopital's rule again, and I urge you to try to do L'Hopital's rule until you can see what's going to happen and convince yourself what's going to happen. I'm going to just jump straight to the point in this video, but you can pause the video and try it yourself. This is going to be a never-ending process of infinity over infinity if you just keep on doing L'Hopital's rule forever. It's never going to stop, and that's not good. So we need to go back to chapter 1, which is what else can we do when we have an indeterminate form? And the next biggest thing after plugging in the thing is do something algebraically, see if you can simplify. And here we definitely can do that. We can write this whole thing as 1 over x times x squared over negative 1. We're doing the opposite of what we did before. We're now taking it out of that division and replace it with multiplication. And when we do that, we get an x cancel out, and we are left with just the limit as x approaches 0 from the positive direction of negative x. And that is just going to be 0. No indeterminate form. So these problems can be tricky because there's no set recipe for how to deal with these problems. We use L'Hopital's rule. We did some algebraic manipulation to do that. Then we actually reverse that algebraic manipulation just so we can do a limit regularly. So there's one example of doing that 0 times infinity, and we'll see more examples in the next video. Last example is, let's do this limit as x approaches 0 of x to the x. And actually, I think we're going to want the limit as x approaches 0 from the positive direction. Yeah, so let's do that. Limit as x approaches 0 from the positive direction. If we plug in 0 into the function, we get 0 to the 0, which is an indeterminate form, but again, we cannot use L'Hopital's rule yet. So this is one of those exponentiation indeterminate forms. We can use the log trick, and we'll try to do it both ways to show what's going on. All right, so one thing we could do is we could just take the natural log of the whole limit. So we're going to go natural log of the limit as x approaches 0 from the positive direction of x to the x. But note that we can write that as just the limit as x approaches 0 from the positive direction of natural log of x to the x. So the reason we can do that is because natural log is a continuous function, and you could just write it like that to begin with since natural log is continuous. So why is this nice? Note that, first of all, we can't just randomly do something like taking the natural log. We're going to have to undo that process at the end, and we'll see that. But let's just say if we did this, something nice happens. And that is we can use the log rule that we can bring this exponent down out in front, and we can rewrite this as the limit as x approaches 0 from the positive direction of x, natural log of x. And conveniently, we just did that problem in example 3 right above. So we have used the natural log to turn this into a problem that now we can deal with. We had to do more algebraic manipulation to deal with, but we found just above that this is equal to 0. So we can say this is from above. So importantly, that is not our answer. Because we can't just take the natural log randomly, we have to cancel it out. And then to get rid of this, we're going to say that our answer is going to be e to the power of whatever we had. And that's to get rid of the natural log at the beginning. This is equal to 1. And that's our answer. The reason we can do that is because if we take e to the natural log of the limit to begin with, then we just get the limit itself. And that's how I like to deal with this limit. And I'm going to show just kind of how to do that on the next page, because you don't have to remind yourself to do the e to the power thing at the end. So you can definitely latch onto this, that's fine. I'm going to show you just a slightly different way to kind of deal with it. And that's going to be that our log trick is going to be to say our expression, whatever it is, our limit. I'm going to write it as expression because it can apply to more than just limits, is equal to e to the natural log of the expression. And we know that's true based on our rule that x is equal to e to the natural log of x. And it really is something is equal to the e to the natural log of something. That's always true. They're inverse functions. So our log trick will be to write this limit as e to the natural log of the limit And the only other real detail here, the reason why people may not want to do this is because it's going to look more complicated. And the thing that we can do is we can bring the limit out in front of everything and write this as e to the natural log of, in fact, I don't even want to bring it out that front, sorry. I'm going to write this as e to the limit as x approaches 0 from the positive direction of the natural log of x to the x. Same kind of thing we did before. And this is because natural log is continuous on 0 to infinity. So as long as we're above 0, then this works. And we're always going to be in these kind of problems. So note that now we have e to that limit, and this limit is exactly the problem we did before. I should write down one more step, I guess. This is going to be equal to e to the limit x approaches 0 from the positive direction of x natural log of x. That is our log rule that we're using, that we did before. And note that this problem we did on the previous page. Now the equalities make a little bit more sense. This is going to be equal to e to that whole limit, 0, and then we get our answer of 1. Note that the last two things we did are really the exact same problem. We're really doing all of the same work. It's just about how you're organizing your information. Do you want to put that e to the power of thing in each step of the way, or do you want to remember to do it at the end? There's positives and negatives to both. I don't care which way you do it. Just latch on to whatever one you feel good with. In the next video, we're going to do a bunch of different practice problems using L'Hopital's rule and dealing with limits in general.